Hello, everyone, and welcome to today's webinar, System Engineering Approaches to Electric Grid Cybersecurity Challenges. I'm Carrie Owens with Internex, and I'll be the moderator for our session today. Before we get started, please know that you could submit text questions to today's presenters by typing them into the questions pane of the control panel. You may send in your questions at any time during the presentation. We'll collect these and address them during the Q&A portion. Once this webinar concludes, all attendees will receive a follow-up email within 24 hours with a link to access the slides and a recording of the webinar. And so welcome everybody. And with that, I'd like to now introduce our presenters, Kay Steffred, Director of Implementation Services with Internex, and Brian Smith, our Principal Consultant. And with that little bit of an introduction, I will now turn the mic over to Kay. Kay, thank you so much for starting us off.
Good morning. I'm Kay Steffred, and as Carrie said, I'll be presenting this morning along with Brian Smith. Brian and I are both deeply involved with utilities, helping them to implement their grid modernization projects. I concentrate on system engineering tasks, and Brian is currently concentrating on implementing cybersecurity for grid implementation projects. Our overall goal for today's webinar is to present system engineering techniques which can be used to strengthen cybersecurity practices. So here's our agenda. I'm going to be presenting topics 1, 4, and 5, and Brian is going to be presenting topics 2 and 3. So we're going to start with a general introduction to the electric grid. Then we're going to discuss cybersecurity frameworks. And then we're going to move into this discussion of OT cybersecurity architecture and requirements, and then on to vulnerability assessment and testing. And we follow with an example, and there'll be time at the end for questions and answers. So here's the first topic, system of systems. So the electric grid is a large system of systems. And system engineering was designed exactly for a system such as this. It was implemented and developed in order to plan and maintain large complex systems. And surely, as you can see by the screen here, the electric grid is a very large system of systems. And NASA was actually one of the first developers of system engineering, and they used it for both the moon launches and subsequent space exploration projects. I think you'll understand that, those projects were very successful, even though they were very complex, and they were probably some of the most highly technical and most difficult projects that have ever been implemented. And so that's what system engineering is all about, managing these large systems and these large projects. So as you can see from the diagram here today, you see the secure communication flows in blue. The electric grid is actually in the yellow dash lines. In terms of cybersecurity, those blue communication flows, which connect the grid domains such as transmission, distribution, and operations, those provide customers and utilities with necessary functions, but they also allow vulnerabilities. Each of those communication lines is a communication path, and that's a potential location where cyber attacks can be inserted. So utilities, this is a general overview of the number of utilities in the United States, and you'll see that there's 3,100 electric utilities, most customers on the blue portion there are actually covered by IOUs, the 200 large IOUs. The reason why that 3,100 number is significant is because that's 3,100 locations where cyber attacks can be inserted. There's a lot of vulnerabilities there with those 3,100 utilities. So if 99% of the utilities have excellent cybersecurity, that still means that 1% or 31 utilities would be very open and very vulnerable to an attack. So what's happening right now is the internet is being used to communicate with virtually all devices, whether they're in the home or even on the distribution lines. Internet protocols are being introduced for distribution sensors. And what that means is systems that were previously very well isolated with SCADA systems, there are maybe a few what we would call backdoors for vendors to be able to come in and examine their systems remotely. But in general, the systems were very isolated from the internet. But all of that is changing now, particularly with grid modernization projects. They seek to those projects seek to be able to communicate to devices on the internet, such as smart inverters, for example. So utilities want to be able to send and receive commands to those smart inverters, but to do so, the inverters are on the internet and they're controlled by non-utility players. And so that's increasingly causing concerns, certainly in the cybersecurity realm, as all of those new systems are going to be potentially methods for attackers to insert attacks. So IT traditionally is in charge of cybersecurity at utilities and most other organizations as well. But there's a lot of differences between the cybersecurity that IT organizations implement versus those for OT. So IT, for example, is concerned with protecting the company's websites and their emails from huge numbers of emails and accesses on the web. And they have, thousands and thousands every hour of legitimate business emails, for example, that need to be examined for threats. But OT is a different world, and it needs a different kind of cybersecurity. And so the challenge for utilities is they need to have experts and they need to be capable of protecting both their IT and their OT environment. And there's a lot of differences in a system that will, and processes that will work for IT won't necessarily work for OT. So, for example, large complex passwords don't work well with operators. If they're critically need to log in, having a large complex password that they can't remember, perhaps can't easily get a hold of their IT folks with, a reset, that's an issue. And SCADA systems simply can't be backed up. IT's number one method of fixing a cyber attack is to simply take the compromised component offline and insert a backup for it. But that's not going to work on SCADA controlled devices at all. And so the tools that are appropriate in the IT environment are just not appropriate for the OT environment. And a lot of what we see in utilities is this difference in friction between the two organizations. And so that's one of the key areas that need to be addressed when you're implementing cybersecurity. And here's a summary more from Idaho National Labs on security threats that are being faced by electric utilities currently. As we talked about, the growth of networks and communication protocols are, much increased potential for cyber attacks. And utilities are not simply being attacked by, typical attackers who are looking to secure money by encrypting all of a company's assets, but they're also trying to actually bring down the power grid. And these are not small organizations. Clearly Russia, China, and Iran have been caught trying to attack electric utilities. These are very well funded and they have mass assets. So they clearly are able to pose a major threat to electric utilities. And utilities often lack, this is what Idaho National Lab says, utilities often lack the full scope perspective of their cybersecurity posture. They're not aware of all of the vulnerabilities and threats. And the staff is also lacking in capabilities. But I don't necessarily know if it's lacking in capabilities. I think a large part of the time is they simply lack enough staff. There's a shortage of cybersecurity experts, both the electric utility and all other industries. And so a lot of times there's just simply not enough people to perform all of the work that needs to be done. So that's the summary of the introduction of cybersecurity in the electric grid environment. And now we're going to move on to Brian, and he's going to be talking about cybersecurity frameworks.
Next slide. And so whenever anybody starts getting immersed in this, wonderful world of cybersecurity in the utility industry, the subject of frameworks is often some of the early discussion or whatever. And frameworks can be a little bit challenging because there are just so many of them out there, and a lot of the frameworks are created for different focus areas. And so if, understanding, what your ultimate goal is and selecting the right framework, is a big challenge for a lot of folks in the industry, because if you pick the wrong framework, you can get, beneficial results out of it, but it may not get you to the extent and to the specificity that you really want it to in the exercise, and it can come across as really not a wasted effort, but an effort that really wasn't proven to be valuable. And so one way of looking at it, is kind of three different tiers, kind of that we've broken down into. You've got frameworks that really are focused on measuring and assessing and quantifying risk. And here, an example here might be kind of the NIST suite of special publications around risk, assessment, risk, and which are fairly common known in the overall cybersecurity world. And these are typically generic IT centric, kind of works. The next level down are frameworks that really focus on the programmatic standpoint of running a security program, either building a security program, measuring, the effectiveness or the maturity of the security program. And these frameworks tend to look at, behaviors and habits, if you would have it. Because at the end of the day, you can build a secure system, but if you don't operate it in a secure manner, you may not be as protected as you think you are. So these program level, cybersecurity frameworks have a very important role in the big scheme of things. But if you're down trying to do more of the system design, system implementation standpoint, they still may not really quite give you a lot of value. And some examples here are obviously they're really specific to the electric sector. We've got, the NIST framework for improving critical infrastructure cybersecurity, commonly known as CSF. And then another work by DOE is the electric sector cybersecurity capability maturity model, which is a mouthful, commonly known as ESP2M2. And then, kind of a lot of the focus that we're going to be talking about today is really this level that we really call the controls and requirements, frameworks. And they really provide, catalogs of controls, that some of them provide methodologies of, applying the controls, but they give you, some more, kind of a starting point of how to build that secure system. And so some examples here, IEC 62443, which is, becoming more and more common in the industrial control system space. NERC SIP in itself can be considered a framework. There's a lot of compliance elements of that one as well. The NIST IR 7628 Smart Grid Cybersecurity is another good framework. NIST SB 800-53 is probably the standard common one that everybody knows of, more of a general IT practice, but a good work to really look at things from a broad standpoint. And so, one thing about using a lot of these frameworks is really understanding how to assess risk, because risk, even though it's kind of a separate exercise, assessing risk helps you understand how and to what degree a lot of these controls need to be implemented. Just because there's a vulnerability discovered in a system, if the risk is very, very, very low, you need to understand that so that you don't inadvertently allocate excessive budget to fix a problem that might not be there when there was a more high risk problem that needs to be accounted for first. And so the biggest challenge we've seen in these OT operational technology environments is it's just not effective to try to calculate and quantify risk the same way that it's been done classically in the IT environment. It really the methodologies don't work well. They don't yield the tangible results, and they really a lot of times are focused on the vulnerabilities and attack vectors, and don't really focus on the impacts. And impacts, in the OT world are about safety, operational risk, compliance impacts, and things like that. And so, understanding how to quantify risk in maybe slightly different terms for the OT environment ultimately helps drive a lot of decision making downstream. And one of the most important ones is where to spend the dollars. Next slide, please. So in some of the works we've done, here's just an example, and this is by no means the only way of looking at it, but it's a very simplistic way of quantifying risk that is effective to communicate outside the security realm, outside the IT realm, really to kind of the key decision makers in the utility in your company, and it quantifies things down to is there a safety impact, potential safety impact, because a lot of these OT systems do have safety related functionality in them, and so first and foremost most any safety potential safety risk quickly gets elevated to kind of that critical impact level. Rarely do you find something that's safety related that you can spin off as a low potentially low impact area. There may be operational one way of looking at things, maybe looking at the operational state of the grid. Does this impact potentially destabilize the grid of some sort? Does it drop load? Does it drop generation? To what extent? And then obviously in some of our NERC focused utilities, there's obviously compliance implications that in the NERC world we know can have direct tangible financial impacts. And so one way of looking at it might be compliance. And at the end of the day, yours may look different than this. They may have different weightings, but it's a quick and effective way of kind of quantifying that risk. All right, next slide. So when we really focus on developing that architecture and controls, the methodology we like to kind of promote in a lot of the practice we do is, and it's really a combination of picking the right framework and understanding the right approach how to use the framework. Just because you've got a framework doesn't necessarily mean you're home free yet. And so the framework provides you a lot of high level guidance. It might provide the catalog of cybersecurity requirements, but it may or may not really give you a lot of tangible ways of how to apply it. It may leave you hanging to try to figure it out on your own. And so that's where kind of the approach comes in. And in the system engineering world, there are many, many, many different types of approaches that one can kind of employ. But three that we kind of gravitated toward using in our past work with clients, and a lot of them are driven by the specific tasks, the resources available, the time available. The approaches are really where some of the challenges and some of the other efforts come into play. And so whether you're trying to assess and improve, modify or improve an existing system, or whether you're building a new system from scratch, these kind of approaches still work, in both scenarios. There may be like caveats where in one versus the other, but in the end, I think these can be used quite effectively in most kind of scenarios. Next slide, please. And so, first we definitely want to start with using a framework. And why are the frameworks so important? And it just like anything else we do kind of in the engineering world, having kind of a structured methodology of kind of attacking the problem is really the first place you need to start. Because if we don't, and we don't use some sort of structured methodology to start looking at requirements, looking at controls, you're really victim of the skill set, the expertise, the experience of the group of people you have working on at any given time. And so that kind of ad hoc sometimes methodology tends to leave gaps in coverage. It tends not to be repeatable if you're trying to really run a security program and you're doing some of these a few years on the same systems. You want to be able to repeat those results and be able to use previous results with the current results to try to benchmark and prove you're heading in the right direction. So if you're just doing everything in an ad hoc method, chances are you're never going to be able to really effectively measure progress, in that respect. And so, and at the end of the day, you really need to address a whole wide variety of topics. And typically, even the best of security practitioners, if you set them down and just, start with, um, a blank sheet of paper, the coverage is not going to be there, as opposed to kind of using one of these frameworks. And a good example here, NIST 800-53, has 18 different control families, and chances are none of us are going to think of every scenario in one of those control families. And in the end, those frameworks have been well vetted by a lot of folks in the industry, so that they have a very good broad coverage of things. They have a depth of coverage, and they give you kind of the best starting point. And at the end, it's that balance of security controls that really are going to drive the effectiveness of the solution. An example is, you are heavily weighted toward all the preventive controls, but you have very little controls or features to be able to actually detect breaches, and even fewer to actually react to, and respond to breaches, then you're kind of weighted in the wrong direction. Yeah, you think you may be protected, but you can't validate it, and you can't maintain that. So having a balance of different types of controls and different focuses is definitely key. All right, next slide. And so the approach is where things kind of get you into your kind of own soul searching, because even though frameworks are out there and very well published, approaches are tend to be very very personal thing for a lot of people. There's no standard approach applied to most any of these frameworks out there. There are some that provide some guidance, but in the end, how to apply these frameworks is kind of a one-on-one decision when you're starting the work. And so the way we've kind of broken down these approaches in kind of three categories. The most common is if you select a particular framework, there's probably some basic native type approach embedded in that framework. The NIST IR 7628 is a good example. Not only do you have a good catalog of controls, there are some basic guidelines in there of how to take that and apply it to your system, and at the end, it results in these particular, cybersecurity controls should be relevant to, these components or data flows in your system. Other methods, depending on your resources, are you tend to have a, what's referred to a lot of times as a top down, and top down really starts with emphasizing the functionality and the purpose and the technology of the system itself, and starts analyzing it that way to look at, things like failure modes and other things to come up with cybersecurity controls. And then you have kind of a bottom-up or a basic approach where, groups have, very effectively gone out there and they've looked at a lot of common vulnerabilities, a lot of the common attacks, and they've come up with kind of a generic set of, controls that you can apply and, start, and gives you good coverage to start with most anything, but they're fairly generic and, they're not really rooted to the system itself. All right, next slide. And so talking a little bit more about the top-down approach. And really here, it's based on the system functionalities, based on the system architecture. It looks at the technology utilized. It tends to be resource, intensive, because you're doing a lot of detailed analysis, because it's a highly customized, exercise. A lot of times this particular method you only see when you're really deploying newer systems, because, it may, a lot of times, this results in not only network and other external security controls, but it results in, cybersecurity requirements for the actual functions and nodes and devices within the system. And so a lot of times, if you're talking about a deployed system, chances are you're not going to get the, opportunity to upgrade a lot of components and do, and change out components. You're really kind of living with what you got. Whereas if you're deploying a new system, you've got more of a chance of actually influencing, the procurement of the system itself. And, a lot of this stems around a very detailed, vulnerability failure analysis. In the end, you want to understand what the system does, what the critical functions and steps are in that system, whether it's, nodes that process data or provide some function, whether it's data flows between two nodes. You kind of build that picture, and then you very effectively go down, line by line, analyzing, what could prevent this function from happening? What could prevent this data flow from happening? And, is what type of attack could yield that impact? And so what control could I put in place to prevent that? And so that's kind of how some of the failure mode and effects scenarios play out. In here, the primary security controls are driven by these failure modes that have been identified. A good example here is some work that Internet's kind of led a few years back under the brand of ASAP-SG, Advanced Security Acceleration Project for Smart Grid. And ASAP-SG kind of looked at different system types within the smart grid, whether it's substation automation, distribution automation, AMI, and broke those systems down and understood what security controls were very unique to those environments versus trying to say, here's a standard set of, cybersecurity requirements that should apply to a SCADA system, an AMI system, a distribution management system, or even a third-party billing system. And in the end, it really just doesn't work that way. All right, next slide, please. So here's kind of an example of what you might do in this top-down approach. You really, want to, map out the system, understand, components, component placement, data flows between components to understand where the critical elements are. And to some extent, you're trying to think like an adversary in this point, to provide the biggest vulnerability, the biggest weakness, what's the softest target, things like that. And so being able to, build these pictures and build the system, effectively helps you understand, where those vulnerabilities are, where the controls can be applied, where architecture needs to be implemented to be able to compartmentalize things, segment things from one another. And so these are kind of the start of these top-down analyses. All right, next slide. And so we talked a little bit about the native framework approach. These tend to be easier on resources. The native frameworks tend to be a superset of industry expertise. And so you may have something that, like NISTR 7628 that is developed for the smart grid, but all the people that really had, input into that work really brought a lot of different scenarios to the table, and it kind of becomes a superset. So it's almost a given, no matter what framework you pick up, some parts of that framework have been influenced by things that really don't apply to your system specifically. But the framework really gives you no way of, filtering that out. And so when you use the native framework approaches, you tend to bring all the controls with it, and you may have controls that really aren't, effective or aren't relevant to your particular technology, system architecture, things like that. There again, they typically don't map one-to-one to any given system at any given day. And the security controls here tend to be categorized or tend to be determined by some sort of basic categorization of your system or system components, things like that. And there again, here, probably one of the most common examples in our industry is NISTR 7628, which has been developed specifically for smart grid. All right, next. And so the last, we really talk about a bottom-up approach. And bottom-up approach really is looking at really a lot of common vulnerabilities across, IT, OT, systems as a whole, and coming, and you start with a basic set of controls that should be relevant for any given system, and you kind of apply those controls, not blindly, but you just assume, they're relevant. We need to basically on a known set of attack vectors. There's very little analysis done of your system you're trying to apply it to. It's really about, putting this security control in place. And if you're in a pinch, if you've got limited resources, these are very good places to start from. I don't want to diminish the value of the bottom-up approaches. All of these really have times and places where they are the most effective way of doing things. And so it really, comes down to your specific, scenario. They could be used as kind of off the cuff, quick assessments, back of a napkin type assessment of existing systems. They just want to kind of get a good look and feel for, are there certain elements missing in our current system? So you might use one of these to, to do some basic gap analysis, things like that. A common one here is, the CIS top 20 critical security controls. A lot of people refer to it as the FONS top 20, but they, these have been, very well vetted, and to some extent, you should see, these controls in any given system to some extent, but in the end, this framework really just gives you a very basic control and no guidance on how to apply it to your system, where to apply it to your system, what technology to use to apply it. So it's kind of, really just a starting point. All right, next frame. So the last, no matter what approach, no matter what framework you really utilize, in most cases, you're still going to come up with a very high-level security requirement written relative to the system. And so at the end, when we're building these systems, when we're doing system engineering, we want to come up with some very detailed plans of how to implement these things. And so the last gap between this list of security controls we now have and the actual implementation comes in the form of tailoring is kind of the phrase that I use from time to time. And it really takes this generic language, cybersecurity control in it, and it either rewrites it or tailors it to your specific environment and underlying technologies. And so processes, functions, things like that, it really makes it more specific. In the end, if this is a new system design, you're also got some need to be able to develop, system or device type procurement requirements. And that's another gap that really the frameworks leave is, you can't really take the output of one of these frameworks and approaches, which is a list of security controls, and attach it to a procurement spec for a SCADA system or for a substation automation system or for a relay or for EMI, because there's going to be no way of really telling of this security requirement. Is it supposed to be implemented in the device? Is it implemented in the network? Is this an application level requirement? And so, understanding how things are written or how to write things for security requirements are a very, very important step in definitely new system procurements. A common example here is, and it sounds absurd, but we've seen in the past where literally procurement requirements have had things such as the system must be NERC compliant, and that's the whole extent of the the cybersecurity requirement, and it breaks down nothing to give that vendor any guidance on exactly what you're expecting as a utility. It gives you as a utility or an integrator nothing that you can dig in and enforce from a contractual basis. So tailoring is a key step to evolving to real security requirements for devices. And then with that, I think I will turn it back to Kate.
Thank you very much, Brian. So now we're going to move into vulnerability assessments and testing. So our first slide here in this section, it shows a comparison of which assessment techniques work best for OT and which work better for IT. And then there's also an assessment of the risk to the environment. In other words, how disruptive would this be to my OT or my IT system? So for example, an example of a high risk to the OT system would be a penetration test, which might really disrupt your operations. So that might not be a great technique to use. For example, in the OT environment, the last thing you want to do is cause any issues within your operational environment when your operators are trying to control the system. So what this is trying to show is, there's different levels of risk, and you should be cognizant of the impact to the IT and the OT systems, and select the assessments that make the most sense without unnecessarily jeopardizing your environments, either the IT or the OT. Now we're moving into some techniques that are system engineering techniques that can help with. So Brian was talking about how the NERC requirement, for example, that it be NERC compliant is not a good requirement. So one of the techniques that's really common in system engineering is a requirements review. And so the first thing you should do is actually document the NERC requirements that apply to your system rather than just say NERC compliant, so that your vendors can actually see the requirements that you intend for them to implement. And you need to make sure that those requirements are defined relative to your utilities or your organization's goals. So one thing that is a very good technique that I think works well is to have your security goals and requirements defined for both IT and OT systems, and have a master set of those that then can be supplied. So when you're going out to for an RFP, you've already got the security requirements defined and where they apply, whether it's the IT, the OT, or specific situations. And then when the RFP needs to be issued, you merely select the correct requirements and send those out with the RFP. You do also need to be mapping the requirements to which systems. So for example, a general requirement might only be applicable to your EMS, for example, and not other systems, so that you need to understand which systems our requirement applies to. Now, I already talked about the RFPs. Another thing that system engineering does is identify gaps and incomplete and missing requirements. A lot of times people will get, as Brian was talking about, some of the requirements, but not all of them defined. And so that's one other thing that system engineering is very good at, identifying gaps in requirements. It also identifies what we consider, like untestable requirements. And that's either a requirement that's too broad or is just plain, can't be testable. In other words, the cybersecurity interface will be user-friendly. Sometimes a type of requirement you see that is completely untestable. There's no definition of what actual screens you're talking about, which GUIs you're talking about, and there's no definition of user-friendly. So those are the kind of gaps that the system engineering requirements review can identify and correct. Another review we recommend is an architectural review, so that you look at all of the access points where the information flows are. For example, Brian showed you the information flow for the smart meters. This helps you identify where you need to put your cybersecurity controls. Where do your DMZs need to be? Where do you need to put in the various components of your solution? Ideally, you'll be able to acquire stakeholder support with this method as well. So if you have an architecture review and you have agreed upon methods of how you're going to protect your IT and your OT systems, for example, what kind of controls are necessary in the OT environment? What kind of firewalls are needed? Do you need a intrusion detection and prevention system? What is your organization's policy for those connections? That helps you, I think, to reduce the conflict between the IT and the OT world in terms of what the correct solution is. The architecture review is generally relatively quick and can be performed once you've got there. As long as the architecture is actually defined, it can be performed quickly, and I think that can be one method of shoring up your security. A penetration test is a very popular method of using. One thing that we, as we showed in the assessment, is perhaps not the best technique for the OT environment. Another thing we see is that penetration testing sometimes is done at a relatively quick and dirty method to the lowest vendor. And what happens sometimes is when they see the pen testing organization identifies one threat, that they find one vulnerability, they find maybe two, and then they simply stop. What we would definitely recommend is that they attempt to identify all of the vulnerabilities, not simply the very first one they did, which technically satisfies their contract. And so that's a recommended technique. Next up is, this is a cybersecurity capability maturity model that was done by the DOE. And I think it helps in terms you do want to on maturity of the processes you have in place. It's pretty well thought out, and it'll give you, I think, a pretty good idea of your organization's preparedness to deal with cyber attacks and breaches. They, like all capability maturity models, they use questionnaires, and they talk, maybe directly sometimes to your staff to determine what policies you actually have in place. And then they give you a score. The advantage here is that you have a metric to use, both to present to internally to your organization, and also as a basis for improvement. So when they identify weaknesses in particular areas of your security preparedness, then that helps you to improve that area, and consequently you can monitor that and monitor your progress with the scoring. This is a standard kind of system engineering approach to how requirements should be verified. So obviously everyone's familiar with the NERC requirements. What a system engineering approach would do to this, it would map those requirements directly to the systems that were applied, to how you were going to provide evidence that has been implemented. It's going to list the responsible organizations. It's going to list the exact person with that contact information. It's going to list the title of the evidence, the location, and ideally a link to the actual evidence that's going to verify that you're meeting this NERC requirement. And what this does is really help with audits and also to identify gaps. So if there is no, for example, evidence that a system is meeting the requirement, then obviously that's a gap. But also, if there's a link to the evidence, then that's a really solid evidence that you have, in fact, correctly implemented all of the requirements onto the systems that are applicable. Okay, next up, we're going to move up to some more examples. So this is, it's not just us who are saying that there are cybersecurity approaches there's system engineering approaches to cybersecurity. This is NREL's definition of their 10 steps. And they, like many system engineering cyber approaches, they divide the space into, 5 or 6 categories. NREL happens to use identify, protect, monitor, respond, and recover. And then they have a 10-step system engineering process. I'm not 100% in agreement with their process, but it's showing that that system engineering techniques do in fact have applicability to cybersecurity. I do like some of their things. For example, the fault scenarios, I think, is a good idea to analyze, develop fault failure scenarios with mitigations. A lot of times, testing only shows, or analysis only shows that a requirement is met, but it doesn't cover the negative case. What happens if something failed? So, for example, if the attackers didn't penetrate one system, say your firewall, what would be the results, and how would the remaining systems help to block the attack? And next up is summary here. And so this is our overall summary of how we think that cybersecurity can be improved with system engineering techniques. We talked quite a bit about the requirements, ensuring that the requirements are documented and mapped. You want to have a consistent set of cybersecurity requirements in all your RFPs. That's why we recommend that you have them documented for both the IT and the OT, and you have criteria on which requirements apply in which situations. I think one thing that can be very effective is to have cybersecurity use cases. So you basically have use cases that define the roles of attackers and defenders, and you go through a sequence of steps that an attacker would try, and then the sequence of steps that you would use to block the attack. We talked about architecture. There are standard reference models for architecture, particularly NIST. In the first slide, we had the overall NIST high-level architecture. That's shown there on the upper right, the distribution and transmission and the blue communication lines. NIST also has many more detailed levels of this. So they go down into details for each one of these systems, and that's a good place to use. To start with an architectural model. One of the techniques you can use is to use their model as a reference and then map your systems to the model. That helps to identify gaps, and it also greatly speeds up the process of documenting the cybersecurity architecture and the architecture in general. we do believe that architecture is one way that can help coordinate and have your IT and your OT organizations working together. If they can agree on the correct architecture for cybersecurity solutions, then I think that's a big step forward to reducing some of the conflicts we see between those two organizations. And it is important when you're talking to the IT and the OT staff that you do understand that they face very different threats and they need different cybersecurity solutions. And being able to recognize that each group has concerns and they need and has different problems and needs different solutions, I think also goes a long way to ensuring that your IT and OT organizations work well together in terms of cybersecurity. We do think you should actively test cybersecurity requirements, and we talked about leveraging requirements, enterprise architecture, and testing artifacts. A little bit more about that is a lot of times system engineering enables you to use the same artifacts for multiple purposes. For example, if you're developing tests for your systems, they can also say you're going to test the operational system of a new ADMS. The testing that you do to verify the correct operation of the system itself can also be used to ensure that the training is adequate for the operations, to ensure that the cybersecurity is adequate, and to reduce the amount of effort greatly. So instead of having one team working on verifying that training is correct and another team verifying that the system is correct, you can have an integrated team that does both of those. Okay, and so that's the end of our prepared slides, and we now have time for questions and answers.
Yeah,
Carrie, are there any
thank you,
questions?
Kay. Appreciate that. Yeah, thank you. We do have a couple questions, and just a reminder for everybody on the line that you can still submit questions for the next few minutes. So if you've got one you want to get in, please go ahead and submit. Yeah, a couple questions for us. Where can we find out more about the ASAP SG security profiles you mentioned?
I'll take that one. The ASAP SG security profiles, the effort was turned the works over to a group called OpenSG, used to stand for Open Smart Grid. That group, unfortunately, has been very dormant for the last little while. So the works have just kind of sat out there, and they really are hard to find these points. But we can definitely provide links to these documents if you like. You can just email myself or Kay, and we'll definitely point you in the right direction. Like I say, they're a few years old now, but they have some very, very good analysis. And the good part about some of our industry is that these systems tend to not to evolve very rapidly. So the underlying system analysis that we've done and the failure analysis, a lot of them are still very relevant today. And so I think they can be definitely good utilized in cases. The ones that were done out there were there was profiles done for substation automation, for distribution management, distribution automation, third-party data access between on the retail side of things, AMI, and wide area situational awareness and monitoring protection. And so there's the security profiles were very, very focused on specific types of control systems. All right.
Thank you, Brian. And then the last question, where do technical standards fit into the cybersecurity framework picture?
That's a very good question. Go ahead, Brian.
No, go ahead, Kate.
So most of the technical standards are at a level just below the cybersecurity controls framework and are relative to specific implementation of a security control. So for example, if one of your security controls is for authentication on a data flow between an RTU and a SCADA master, then IEEE 1815 DMP3 would be used to guide the implementation of the specific technology associated with DMP3 secure authentication. And that's similar for most of the protocols. Any more questions, Carrie?
Thank you, Kay. One more just came in. Let's see here. Can I do my own cyber maturity assessment, or should I have some organization do it?
do either. Many people like to do a preliminary assessment on their own and then see how they score. And then other people prefer to just call in the maturity assessors immediately. I think either one would work. I certainly don't think you need to hire somebody else if you're not necessarily going down that path. You can definitely do the assessment yourself, at least initially.
Okay, thank you. And I think that will wrap our Q&A portion. And then just a couple concluding slides. Just a thank you to each of you for participating in our webinar today. And if you do have additional questions, feel free to email Kay or Brian. And we also invite you to visit our website at www.internex.com. We have a wealth of complimentary resources in our knowledge base available to you. And be sure to connect with us on Twitter and LinkedIn as well if you don't follow us there. Once again, you will receive a follow-up email shortly with a link to the presentation slides and a link to the recording of the session. And with that, we will conclude. Thank you for joining us and have a great rest of your day. Thanks, everybody.